And now we have, last but not least, the first Clarke Prize winner, Professor Bruce Rittmann from Arizona State University. Professor Rittmann is well known for his pioneering contributions to the fundamentals of biofilm processes, and this stimulated the widespread applications of biofilms for treating contaminated waters, soils, and of course ecosystems as well. I don't have time to list all of his awards, but let me just mention a recent one that is quite significant. He got the inaugural ISME IWA BioCluster Award for his leadership in promoting interdisciplinary research between microbial ecology and water and wastewater treatment and reuse, which is very important. So he's going to tell us today about how to use biological processes to treat oxidized pollutants. So please help me welcome Professor Rittmann.
Okay, good afternoon. Thanks for sticking around. Earlier, George Chabanaglos expressed solidarity with me for not wearing a tie. I want to thank George for that. I would explain, through the largesse of Southwest Airlines, my bag got to spend a romantic night in Nashville. And I'm hoping it will be joining me any minute now. I really hope so. Okay, so I'm going to be talking about detoxifying oxidized contaminants here, and I want to start with some acknowledgements. In August, I participated with these fine fellows in a workshop on this topic at IWA Biofilm Conference in Switzerland. So Dr. Jess Brown from Corolla Engineers and Dr. Rob Nierenberg from Notre Dame University and myself, we led a workshop on reducing oxidized contaminants in the drinking water setting. So, in fact, most of my talk today is really going to be the outcome of that workshop. So let's begin by defining some terms here. This is my title, Detoxifying Oxidized Contaminants. So let's define the terms. So the first one is contaminant. You know what that is, harmful water pollutants. Second term is oxidized, and I'm using this, of course, in the chemical sense. An oxidized material is one that can receive electrons and then becomes reduced. I'm going to show you some oxidized contaminants in a minute, but there's a common characteristic of all of them, and that is they can be reduced by bacterial action. And this is, so we want to reduce them and they stop being contaminants. Just for context, you're hearing a lot these days about biofiltration in drinking water treatment. It's a great thing to do. But that is sort of the other side of the coin. And there we're taking reduced materials like biodegradable organic material or ammonium, and we're oxidizing it. We call that removing biological instability. Here I'm talking about reducing oxidized contaminants, and when we do reduce them, or well, the microorganisms reduce them, we just help. We create harmless or easily removed materials. That is, we have detoxified the contaminated water. So I'm going to give some examples, lest you think that this is not a very widespread issue. There are many oxidized contaminants. We'll start off with the most familiar, that's nitrate from agriculture and wastewater. That's the bad news. There's a lot of it around. The good news, it's really easy for microorganisms to reduce this to nitrogen gas. Perchlorate, that's a hot one around here. It comes mainly from rocket fuel, and it can easily be reduced to chloride and water. Selenite and chromium are two materials from coal-fired power plants and mining and metals industries. Serious problems. But they can easily be reduced to solids, elemental selenium or chromium oxide solids. Chlorinated solvents like trichloroethylene, TCE, common in the semiconductor industry, metals, dry cleaning, used to be in dry cleaning. Really serious carcinogenic materials. They can be reduced also to harmless ethene and chloride ion. Bromate, disinfection byproduct, can be easily reduced to bromide. And then radionuclides, neptunium, uranium, plutonium, exist in the environment in oxidized forms, and they can all be reduced by microorganisms to produce insoluble precipitates that are easily removed. So we have a whole long list of oxidized contaminants. They're everywhere. That's the bad news. And the good news is that microorganisms will happily reduce them if we give them the right conditions. So what are those right conditions for getting the microorganisms to reduce the oxidized contaminants? Well, first of all, we need to create anoxia, or we get rid of dissolved oxygen. This isn't difficult to do, but if you give the organisms oxygen, they'll just take it, and they'll use it instead of the oxidized contaminants. So we got to get rid of the oxygen, but that's trivial. Like in any biological process, we need good retention of the good biomass. We need to keep pH usually around neutral. Make sure there are nutrients like phosphorus. That's normal business, nothing special there. The key thing is we want to reduce these oxidized contaminants, so we need to give them a source of electrons. We must give them an electron donor. And we've got two broad choices. We have organic electron donors. We call that for heterotrophs. Or we have inorganic electron donors, and we call those for autotrophs. Now I'm going to clarify some terminology here. Heterotrophy and autotrophy. So heterotrophy and autotrophy actually refer to the source of carbon that the organisms use. The organisms are about 50% carbon, so they need a lot of it. So heterotrophs are using organic carbon. Autotrophs are using inorganic carbon like CO2 or bicarbonate. Now, the key thing is that in almost all cases, when a microorganism uses an organic electron donor, it also uses the same organic material as its carbon source. And when a microorganism uses an inorganic donor, it almost always uses an inorganic carbon source. So inorganic goes with inorganic and organic with organic. So heterotrophy and autotrophy generally also match up with the electron donor. So what do you need to know, and what am I going to try to tell you today? We're going to try to identify what's the status of the heterotrophic and autotrophic processes that we can use for reducing these contaminants, and some pros and cons of the approaches. So that's the agenda for today. So I'm going to start off with this graphic here. This is one of Jess Brown's I'm using, and he's just illustrating what goes on here with the heterotrophic organic organisms. So you got heterotrophic organisms. At the top, upper left, you'll see a list of electron acceptors, including nitrate and perchlorate and chromium-6, some of our contaminants. Down at the bottom and circled in red is the organic electron donor. And the most common ones used are the two that are shown here, that being acetic acid and ethanol. And then the donor is oxidized, and the electrons are used to reduce the acceptors, and that also to produce biomass, as it's shown here. Now, when you do that, you grow biofilms. Now, here's some pictures of some typical media. I believe this is expanded clay media. In the center of the picture, you just see the plain old media, and then on the right-hand side, you can see the biofilm growing on it. So you actually see the microorganisms beginning to accumulate on this. And if you take and let it grow for quite a while, you can get something pretty dramatic like this. Yeah, there's a lot of biofilm there. And so this is what we aspire to. We want a lot of biofilm in our processes to remove the contaminants. Now, when you're using these organic carbon electron donors here, there's some considerations. On the good side, the organisms can grow quite fast. They have high yields. You can produce a lot of biomass pretty quickly on that. That's on the good side. Of course, that's also the bad side. Then you produce a lot of biomass, and you've got to do something with it. Now, an interesting issue, and this is one I learned from Jess in our workshop, was that actually some of these organic donors can be kind of expensive because in order to use them for drinking water, at least, you have to use food-grade certified chemicals. And it's not so easy to find them, and they can be kind of expensive. So that's a special issue here of using this in the drinking water setting. Of course, if these organic materials aren't all removed and they go out of the process and you then do downstream disinfection, you're going to produce some disinfection byproducts, and that's not good. And you also then have some of these need specialized storage, particularly things like ethanol. Now, one thing that's important take-home lesson is that these heterotrophic processes are out there and available now. You can go out and purchase these systems at full scale. And so here's a picture of a full-scale fluidized bed system from Envirogen. They use granular activated carbon, and similar to what Perry McCarty was describing in configuration, they fluidize this material and the biofilm grows on the fluidized material. You can get very high loadings, high volumetric loadings. It's a very good system, and you can see a picture of a large-scale installation of this Envirogen system. Corolla Engineers has their Biota two-stage fixed bed system here, and the first stage is the anoxic reactor. That's when you add the electron donor and any other nutrients you have and remove the oxidized contaminants. There's then a second stage for aerobic treatment, and I'm going to come back to that point later in my talk. And this is and there's a picture of some large-scale units that are available for the Biota system, and it's also the system that gave us this beautiful picture of biofilms. So that's the source. Okay, now I'm going to shift to autotrophic processes where we're using an inorganic source of carbon, that's CO2 or bicarbonate, and then going along with it will be an inorganic electron donor. So what are our choices? Well, there are three main options available to us. One is hydrogen gas, H2. And then we have reduced sulfur compounds, as you can see listed up here, and at least in principle, we could use reduced iron for this. So those are our options. Now, of these here, the one that's way by far the best developed is using hydrogen, and that's the one I'll focus on after this. So what are the advantages and disadvantages of going with these autotrophic systems? Well, the first bullet here is kind of the opposite angle of heterotrophic. The autotrophic systems have to autotrophic microorganisms spend a lot of energy reducing and fixing carbon, inorganic carbon. And because of that, they grow much more slowly and they have lower yields of biomass. So that is, on the bad side, it takes longer to get the biomass grown. On the good side, you have a lot less of it that you have to worry about, in terms of disposing of biomass or having it in the effluent. All of these donors are sparingly soluble, and particularly hydrogen. Now that's good. Since they're sparingly soluble, you can't really put much in the water. But on the other hand, you have to have special devices to deliver these sparingly soluble materials to the organisms. And finally, they're not really toxic materials, so you're not really dealing with special problems of some harmful material that you're adding to the water. Okay, now I'm going to spend the rest of my time on autotrophy on the hydrogen system here. Truth in advertising. Of course, I'm not going to talk about the system that is my system, and I'm the inventor and developer and researcher on it, so you should know. Okay, so hydrogen. Why use hydrogen? One, it's a relatively low-cost source of electrons, certainly low cost compared to almost all the organics. It has a very high density of electrons per mass. Hydrogen molecule, molecular weight of 2 electrons. It's hard to beat 2 electrons per 2 grams. It can be produced on site, or you can buy it in bulk, and it works to reduce anything that's reducible by microorganisms, what I call the universal electron donor. It always works. So to deliver it, you have to take into account that hydrogen gas is a very low solubility material. And so in the Membrane Biofilm Reactor, or MBIR, this is what I have developed, we deliver hydrogen gas by diffusing it through the wall of special gas transfer membranes. And you can see here a cutaway drawing of it. So you put hydrogen on the inside of these hollow fibers, and it diffuses through the wall, and then living on the outside of the fibers is the biofilm of the hydrogen oxidizing bacteria. They oxidize the hydrogen coming inside out, and they then reduce the electron acceptors, oxidized contaminants like nitrate and perchlorate going outside in. It's a very nice, very simple way to do it. You're delivering the electron donor right to the organisms directly. So here's what it looks like. We have a nice picture of some of these hollow fibers. They're just, in this case, is glued into the end of a pipette. And then that's the left-hand one. And the right-hand one is a stained photomicrograph of one of these biofilms. It's 50 to 30 micrometers thick in this picture. And the dark area to the left is just the membrane wall. Now, this is a well-developed technology by a company called APTwater. They market it under the trade name of ARONITE. ARO stands for Autotrophic Reduction of, and nite would be nitrate. So yeah, they spent years developing this, and they have special spiral round modules. There's a diagram at the top. They weave a cloth of these hollow fibers, and then they wind the hollow fibers spirally around the core, and the water flows spiral through this and past the fibers. If you look into the upper right-hand side, you can see in a pilot unit, you can see 7 of these spiral round modules in a common tank, so you get a good view inside of what these modules look like. And then in the lower left, you can see a picture and a drawing of a full-scale system with lots and lots of these modules in this. And that was taken in Rancho Cucamonga, not far from here. Okay, so I've given you now a quick introduction to the general concept of microbial reduction of organized contaminants, of oxidized contaminants. I've talked about heterotrophic options, and I've talked about autotrophic options, particularly with hydrogen. So now I'm coming to the end here, and I'm going to try to sum up with some key take-home lessons and some issues that are really important for moving these technologies forward so that we can really use them in a widespread way to help us out with our problems of oxidized contaminants. So I've got just a few points here. So the first point, this was the point that came out really clear in our workshop, and it's really clear to me having worked in the development of the membrane biofilm reactor. And this is true for all the processes across the board. Biomass management is critical. You can have too much biomass and you can have too little biomass. Now, if you have too little, you don't remove the contaminants. That's obvious. But if you have too much, it gets in the way. And it can cause excess head loss in the system. It can cause short circuiting in the system. And so it really is a big problem. Now, fortunately, in all the technologies I've mentioned, there are ways to do kind of a backwashing regime here to clear out the excess biomass and prevent this. Now I'm going to show you one diagram here, one graphic from the biota system here showing the value of this backwashing. So here is some data on the, is this for perchlorate removal in the biota system here, and you can see it was going along great for a while, and then the concentration of perchlorate really started to go up. And this was because there was too much biomass and it was getting bad mass transfer, maybe short circuiting. And so they did a backwashing cycle that cleaned the filter, and you can see performance went back to really good. And it happened again, and you had the same result. So this is a case where we're seeing the issue of sort of clogging and poor hydrodynamics. Now here's a graphic that Rob Nirenberg did on the membrane biofilm reactor. And if you look at the big graph towards the right here, what you see is a graph. These are model predictions, but they really match well with reality. And you can see for 3 different conditions that the nitrate removal flux, so the vertical axis is the rate of nitrate removal, goes up with increasing biofilm thickness, hits a peak, and then comes down. And so there's an optimal biofilm thickness, in this case around 50 or 70 micrometers. So it's clear if you have too little biomass on the left side, you don't have enough biomass to do the job. But why is it going down on the right? And that's illustrated by the bottom graphic to the left, which is showing the distributions of hydrogen. Hydrogen is the dark dashed and dotted line coming down from the membrane and going down through the biofilm, and then nitrate coming down the other side. So if the biofilm is too thick, then the nitrate and the hydrogen don't have a very big area where they're simultaneously together at a significant concentration. And you actually separate the donor from the acceptor, and you don't get good removal. So you really want to have very good biomass control so you don't end up with too much biomass. Second issue, accurate delivery of the donor is essential. It's really important to avoid overdosing or underdosing of the electron donor. And this is a particular issue with the organic donors where you have to actually feed in acetate or ethanol at the right amount. And so I'm going to go back then to this diagram of the biota system here. And I said I would come back to this, and now I'm coming back to it. So you can see here, there's a two-step process. The first is the anoxic bioreactor. That's where the nitrate or perchlorate is reduced. And then there's a second reactor, and that's the aerobic biofilter, and that's where the excess organic material is oxidized. And so in order to make sure that there's sufficient electron donor in the first stage, it may be overdosed. But then you've got to remove it in a second stage. So this is a very reliable system here to do that, but you have to take into account explicitly the need to prevent the leakage of a lot of organic material into the final finished water. Now in the membrane biofilm reactor, it's a different story here, and I'm returning to this graphic I showed you before. In the membrane biofilm reactor, the hydrogen is diffusing through the wall of the membranes. And it diffuses because the microorganisms are demanding it. They are consuming it in the biofilm, and that's creating a concentration gradient that pulls the hydrogen through. And so what we need to do in operating the membrane biofilm reactor is we need to make sure that the pressure of hydrogen inside the fiber is enough so that the delivery capacity meets the demand from the microorganisms. We can compute what that is. It's not that hard to do. But we need to pay attention to it. Unless we just grossly overpressurize the hydrogen inside the membrane, we get virtually zero hydrogen in the water. Okay, third, pH control. pH control is very important in any biological system. The organisms don't like extreme pHs. The key thing here in reducing oxidized contaminants is that in most of the cases, the reduction reactions produce base. And that will tend to cause the pH to rise. And so we need to control that in the system here. It's not that hard to do. We now have automated pH control systems in all the systems I've described to you, so it's not hard to do, but we need to do it, otherwise we either get the pH going up too high and harming performance, or we start precipitating minerals that we don't really want to do. Automated operation. We've made a lot of progress in all the systems I've described in automating it, but we need to be going further on automation of these systems. So we need better inline monitoring and just control systems. So this is an area where all the folks who are working in this area are putting some energy in so that we can make these systems reliable and not depending on some operator being there 24 hours. And finally, the last one here is we need to deal with the issue of multiple oxidized contaminants that have to be reduced together. So, for example, when you have perchlorate contamination, you always have nitrate around. So perchlorate and nitrate always go together. Likewise, if you have selenate in the water, you almost always have nitrate together with it. So you have to deal with nitrate and selenate together. We're dealing with a really interesting one right now where the target contaminant is uraninite. That's uranium, oxidized uranium. It's very soluble in the water. We'd like to reduce it to a solid and remove it. But the waters that contain the uranium also contain nitrate almost all the time and often selenate at the same time. So we're now dealing with 3 oxidized contaminants. We have to be able to remove all 3 of these things. So the design and operation of the system needs to be tuned into having multiple oxidized contaminants, often removed by different groups of organisms. It's a huge research area in our center right now. So with this, I believe I have come to the end. So I have just a nice collection of interesting pictures from my talk, and I'll be very happy to address any questions. Thank you.
Thank you very much, Bruce. We did start 20 minutes late, so we're going to have to make the questions relatively quick, and so the answers, please.
Bruce, that was a great summary. About 15 years ago, Rose Trussell and I and some others sat on a panel to help the Department of Health Services approve the fluidized bed reactor for perchlorate. So it's the best available technology for drinking water situations. But subsequently, I've experienced and learned about secondhand, to some extent, situations where the fluidized bed reactor didn't work. It either was unreliable or it had too many upsets, so you had to combine it with ion exchange for perchlorate. So could you talk a little bit about the stability issue with these kinds of reactors?
Yeah, I mean, so there are a couple of issues here, and some of these issues are across the board in all of them. First of all, in general, reducing nitrate and perchlorate is pretty easy stuff. And then same thing with selenite. These are actually very easy. There are lots of organisms that will do it. It's not a problem. So the problem isn't with microbiology or with chemistry. The problem is with reactor design. For example, if you're not controlling the biofilms and you get, usually it's too much biofilm in there, you have lots of problems with flow distribution, and that can cause short circuiting and get very bad performance. We had an example with the Membrane Biofilm Reactor where we, with good intentions to remove more perchlorate, we reduced the loading, and we ended up inducing some sulfate reduction, and that caused some operational problems. So you have to pay attention to them, but they're not fundamental problems of microbiology. They're things of good engineering design and operation strategy on that.
I'll ask just a quick one.
Yes.
You are right about the importance of having just the right amount, but I presume that doesn't mean in terms of stoichiometry. I assume that you mean in terms of relative fluxes to avoid flux limitation of the. How do you determine that?
Well, it's number one. The core is just stoichiometry. All right, so you're going to apply an electron donor. That electron donor does two things. One is it reduces the electron acceptors. That's our oxidized contaminant. Yeah. That's the larger amount. But then there's also an amount that goes to synthesizing new biomass. So you need to be able to estimate the stoichiometry. So that is the number one thing on it. Yeah, you could have some kinetic issues on it, but basically, if you get the stoichiometry right, chances are you'll be very close to where you need to be.
Excellent. Well, if I'm sorry, I'm
That's all right.
blindsided here. Go ahead.
One quick last question.
Yes, sir.
So we've heard a lot about these trace organics and in water reuse systems. What goes into the wastewater may be going into the water. How well do your systems work for some of these emerging pollutants?
You want to give me a couple of examples?
We talk about the compounds that Perry talked about.
Okay, the pharmaceuticals and things like that. Yeah. We haven't looked at them. I don't. My initial reaction is that it's not going to be particularly well targeted towards those. But we've never tried those. So we've tried all kinds of things that are clearly oxidized contaminants. For example, TCE is an oxidized contaminant. It worked.
But you've got a nice active biofilm, and it's quite anaerobic and very reducing, so it might be. It might.
I mean, but we just haven't tested it, so I can't say more than that.
Well, with that, let's thank Bruce and Bruce.